Okay, so we are going to talk about the fundamental theorem of calculus part 2. But before we do, let's review the fundamental theorem of calculus part 1. I have it on the board, but I'm going to go ahead and write it up here too. Okay, so the fundamental theorem of calculus part 1 is when you're taking the derivative of an integral where the lower limit is some constant, the upper limit is x, and the function is f of t dt. So what is the value of that? Like, what is that? It's just f of x. Good. Now the fundamental theorem of calculus part 1 is super easy to do. It's also really easy to overlook. And it'll be a problem that it's so easy to do it, but you're overthinking anyway. So when you have the derivative of the integral, it's probably the fundamental theorem of calculus part 1. Okay, the fundamental theorem of calculus part 2 is different. And so what you're going to do on this one is actually find the antiderivative, like we did yesterday. And so this is saying that capital F of x is the antiderivative of that. And so what you do with the antiderivative is you plug in the upper limit, and then you subtract the antiderivative where you plug in the lower limit. And that gives you the value of the integral. And what is the value of a definite integral? What does it tell you? The area between the curve and the x-axis. Very good. What does a negative antiderivative mean? A negative value? It's below the x-axis. So in a case, it would mean there's more area below than there is above. Good job. Okay, we're going to do this in parts. So we're going to just do all the problems that use the fundamental theorem of calculus part 2 straightforward, and then we'll go to some other things. All right, so sometimes you can be asked to use this theorem with a table. So this table gives the temperature of water in a tub. It is strictly increasing. This is getting hotter. Doesn't make sense, but that's okay. Is the twice differentiable function WT, where values of WT are given below. All right, so we're going to find the definite integral from 0 to 20 of W prime of t dt. All right, so what is the antiderivative of W prime? W. W. And so if we're doing the fundamental theorem of calculus part 2, we find that antiderivative and we plug in the upper limit minus plug in the lower limit. All right, and then we can get those values from the table because this table is W. So that's going to be 71.0 minus 55.0. And that's just going to be 16. And then we're going to interpret this in the context of the problem. So what is 16? It's degrees Fahrenheit.
Would that be
Well, what did you subtract?
subtracted the temperature at 0 minutes from the temperature at 20?
So what would that be?
The difference in temperature?
Yeah. From 0 minutes to 20 minutes. I know. Bless you. And if we think back to what we did when we were remember we were accumulating snow and we were accumulating oil and all that? It's the same thing we just found. So if we didn't even see this, and this was the rate at which the temperature and the water is changing, and we find the integral from 0 to 20, that was the change in temperature from 0 to 20 minutes. We can think about this lots and lots of different ways. All right, let's go on, because that is, out of everything we're learning today, that's the least important thing.
Oh.
All right, so let's look at example 2. We're going to just straight use the fundamental theorem of calculus part 2. So what we want to do is find the antiderivative of 3 dt. It's not x, so you're close. 3t. Now, what is the difference between what we're doing today, like the way this looks, what we're doing today and what we did yesterday? These guys, right? The upper and we were doing indefinite yesterday. And what would we have to do after the t? A plus c. On definite integrals where you have upper and lower, you don't do that. So what you do to do the notation, what I do, is I'll do like this little bracket, and I'll go ahead and put my upper and lower limits on the edge of the bracket. Okay. Then I'm ready to plug those in. So I'm gonna plug in the upper limit for t, and then subtract. And then I'll plug in the lower limit for t. And so that ends up being 30 minus 12, or 18. Now, I tried to make these be ones that aren't incredibly difficult to do without a calculator, because I really want you to practice without a calculator. There was one that I just told you to leave your answer messy because I didn't want you to spend 10 minutes without a calculator on it. But anyway, all that is stuff you could do without a calculator. All right, let's look at example 3. The antiderivative on this one's going to be a little more challenging, but we can do it. So what is the antiderivative of cosine of theta? Nice. And what about 2 with respect to theta? 2 theta. And then we'll put in our bracket with our lower and upper limits. Now we have to plug these into 2 places, which sometimes makes it a little complicated. But we'll take the pi and put it in both here and here. And sometimes I like to use parentheses for it, just for my brain sometimes. Now, doing the second one, the parentheses are going to be important. Then we'll put 0 in for both of those thetas. So what is the sine of pi? Mm-hmm. What about the sine of 0? Mm-hmm. All right, so this ends up just being 2 pi as the value of your integral. All right, you guys feeling okay? Okay, let's do one that might be a little more challenging. Okay, so this one I did go ahead and make it have a power. It's possible on your assignment, I can't remember. Instead of that, it could be the square root of x, where you would need to rewrite it. But let's just go ahead and find the antiderivative. Okay, so I'm going to add 1 to my power, and then I'm going to divide by my new power. So what is my new power going to be?
3 over 2.
We add 1 to 1/2, so 1.5, or sorry, 3/2. We want to do,
I was like, what?
I just heard 1/2. Never mind, I'll tell y'all later, I'm recording. So our new power is going to be 3/2. Writing it as 1.5, I think, is going to mess you up. All right, and then I need to divide by that. And we'll come back to what that means to divide by it.
Actually makes me want to cry looking at it.
It's not hard.
I hate fractions.
What about 2 with respect to x?
2x.
Yes.
So we always put the constant with respect to whatever variable we're
Yes,
using.
ma'am. So that's what this is going to tell you on each one of them, like what the variable of integration is. Okay. All right, so let's kind of clean this up before I start plugging in. So how do you divide by a fraction?
Multiply by those.
Right, so this is really 2/3 times 3. Mm-hmm.
No, I'm just saying it.
See, you love fractions. I don't know what you're talking about.
No, it works over ways too, because you get 3 over 5.
3 over, are you using a calculator?
Well, I know 1.5 is half of
3 over 1.5. Oh, yeah. And you can divide that in your head and
3. I
get
mean,
2?
that one I can.
All right, that's fine. If you want to do it that way, you can. All right, so now I'm going to plug in the numbers. I'm going to start with 9. So I have that 2 in the front. What does it mean to raise something to the 3 halves?
Multiplying it by itself. 3.5
You
times.
square root it and cube it. Or you could cube it and square root it. If we're doing 9 and we're cubing and square root, it would be easier to do the square root first and then cube. So you can do it in any order, but because it is the 1/2, there's going to be a square root, and then I'm going to cube it second. All right, and then I will also put 9 in here.
Wait, why?
Okay.
Why are we cubing in square root?
Okay. So an exponent of 3 halves means you take the
Is
bottom.
this where you kind of do the loop thing that we practice? I feel like.
Maybe. I
feel like
because
we
the
practice
loop is
something.
usually with logarithms.
Oh,
But
okay.
whatever the denominator is, that's the type of root, and the numerator is going to be a power.
Okay.
Does the 3 also go like
Which 3 are you talking about? This 3?
yeah, so doesn't it like the 3 stays on the top of the 2 and then
Yeah, it's the type of root. So this is 3. Is this 3? So raising something to the 3 halves means you're taking the square root of it and you're cubing it, or you're cubing it and then taking the square root. That order doesn't matter. Because it's a 9, I want to square root first so I get a small number, but it works either way. Okay, so we'll do the same thing with the 4. So, what is the square root of 9 cubed?
27.
What about the square root of 4 cubed? 8. So then we're just doing a little adding. If this had been a free response, you would have stopped. You would just stop right here. You actually could have just left it as that power, but we're going to keep going. We're pretending like it's a multiple choice question. All right, so eventually we are going to get 72 minus 24, which is 48. All right, any questions? Now the calculus part was this. Or this right here. The rest of it was algebra stuff and arithmetic stuff. But. All right, all good? Okay. So we're going to go back to the front page. And we're going to take the fundamental theorem of calculus part 2, and we're going to actually solve it for f of b. So if you're going to solve it for f of b, what would you do with capital F of a? Add it. So it's going to be capital F of a plus the integral from a to b of lowercase f of x dx. We use this a remarkable amount of time. It's a really easy theorem to use, but it's also kind of easy to forget about. But it's great, and you use it when you want to find a final amount. So what you do is you take an initial amount. I feel like we kind of have already done this already. And you add an accumulated change to it. And so to set this up, your final amount that you're finding, f of whatever, needs to be the upper limit. And then this initial amount, where that is located, needs to be the lower limit. All right, so here we go. Sorry.
On the initial amount, could we also like subtract the accumulated amount from that?
Yes. Wait. Yeah. And that's kind of what you end up doing. You'll be given a value, like this will be given to you, and sometimes like it's after the final amount. So sometimes you kind of work backwards. It all works out. But this is how you set it up. Just make sure whatever is here is your lower limit, whatever's here is your upper. Okay, so let's look at, this is like a good review question, a good review problem that uses new stuff and old stuff. All right, so we are given g prime of x. We also know what g of negative 2 is, and we want to find g of 4. So what is your final amount going to be? Which symbol, I guess? What are we finding?
G of 4.
Yes. What do we know?
G of negative 2.
Yes. To that, we're going to add the integral. What should be my lower limit? Yes. And my upper? Yes. And then g prime of x dx. All right, so it's important that these are the antiderivative of your integrand, and they are, because this is g prime. Okay. So now we're just going to plug in values. So g of negative 2, I know is negative 11. How am I going to find that integral? The areas, right? Yeah. All right, so this is going to be a semicircle. So 1/2 pi r squared. What's r? Good. So 1/2 pi times 4 is 2 pi. Because it's above the x-axis, it's a positive. All right, this one is going to be 1/2 base times height. Okay. On a free response question, you would just stop right there. On a multiple choice, you would go ahead and combine negative 11 and 2, and that's it. Oh. Well, hold on. Did it wrong earlier. All right, any questions? Okay, and then a multiple choice question. So we know g is the antiderivative of f. We know g of 3 is 5. We want to find g of 8. So what are we going to add? What's the first thing we're going to write after the equal sign? G of 3 plus the integral from,
8 to 3.
okay, 3 on the bottom, right? 8 on the top, okay. And then we know f is the antiderivative. Sorry, we know g is the antiderivative of f. All right, so which choice does that match up with? D, right? Good.
Now, what is the difference between using like a capital and a lowercase? Because I noticed that we switch it up sometimes.
A lot
whenever
of
we're
times,
talking
I don't know, really. I mean, it just uses a different notation. I don't know why. It doesn't have to be capital, but a lot of times the capital is the antiderivative. And sometimes they're the same variable, just capital and
That's what
lowercase.
I've seen
Sometimes
a
it's
lot.
not, but it seems like a lot of times the antiderivative is denoted with a capital G, but it doesn't have to be. Okay, and then let's talk about this. We're going to talk about the fundamental theorem of calculus part 1 again, but just with a little bit of a kink in it. And I'm going to see if we can figure it out without like me telling you what it is, because that's the best way to remember something. All right, so we have this definite integral that's going from pi to x squared of sine of t dt. So let's go ahead and evaluate it. So what is the antiderivative of sine of t dt?
Cosine, negative cosine.
Good job, Keena. So whenever you're finding the antiderivative and there's a co in it, we make sure, sorry, that should be a t. We make sure that we do a negative. It's always, the answer is a negative co. All right, and we're going from pi to x squared. All right, now what do we do with that pi and that x squared to represent f of x? So negative cosine of x squared minus negative cosine of pi. All right, and then what is the cosine of pi? Gosh, that's so many negatives. There's going to be a negative 1 in the end. All right, so that is a way that we can represent f of x. All right, so I know I told you we have to be able to go back and forth between integrals and derivatives. So we're going to find the derivative of the negative cosine of x squared minus 1. So what is the derivative of the cosine of something? Negative sine of something. So if it's already negative, you make it positive of that something. What if that something is not just x? Chain rule. You multiply by the derivative of that something, which is
2x.
Nice job. What is the derivative of negative 1? Yes. Good job. Good job. A lot of times people start going the wrong way. All right, so that is the derivative of this. All right, so let's think about what we did with the fundamental theorem of calculus 1 when it was a number to just x. What did we do? What did we do with the x?